Participants, please fill the attendance provided in the chat box. For session 5,
Kuldeep sir, good evening, sir. Shaila ma'am, Kuldeep sir is there, no?
Yes, ma'am.
Sir, can you hear me?
Madam, I have one question. Hello.
Yes, sir.
Madam, how many attendance you are taking per day? Two attendance, no?
Sir, GMeet itself takes the attendance.
Okay. Now feedback regarding feedback form. You are putting every day. You are putting the two links, no?
Yes, sir.
Okay. Because right now I have seen that four links, so that's why it has confused me.
So the first session, today's first session's attendance and feedback link is there. We will share second session link after or at the end of the session.
Okay. So for every sessions you are taking the feedback.
Yes, sir.
Thank you.
Am I audible?
Yes, sir. Yes, sir. Sir, shall we start?
Yeah, let me share the screen and we'll
Sir,
check
just
once.
wait. We will start from our side. We will introduce you first, and then you can share yours. Shaila
Sure,
ma'am,
sure. Okay.
over to you.
Thank you, ma'am. A very warm and pleasant evening to one and all present here. I, Mrs. Shaila Pawar, on behalf of Information Technology Department at AC Patil College of Engineering, Kharghar, welcome you all to the sixth session of 6 days online ATAL FDP, that is Performance Optimization Technique for HPC Applications. Without further ado, allow me to introduce today's esteemed speaker, Dr. Kuldeep Kurte, a research scientist at Reliance New Solar Energy. He has expertise in applied AI, geosemantics, and high performance computing. Dr. Kuldeep earned his PhD in spatial image information mining from IIT Bombay in 2017 and has vast experience in scalable geocomputation and satellite data analysis. He has worked on scalable geocomputation and energy optimization with prior experience at Oak Ridge National Laboratory, USA. An active ACM and IEEE member, he has contributed to top journals and conferences in his field. He has served as a referee for several international journals that includes the IEEE JSTARS, TGRS, GRSL, and several others. He has served as a referee and programming committee member for several workshops and conferences such as ACM 6 Special, IEEE Geoscience and Remote Sensing Synopsium, IEEE Big Data, and Earth Vision CVPR workshop. Today we will look forward to his insights and expertise. We welcome you, sir. Please accept our virtual token of respect.
Okay. Yeah, thank you. Yeah,
Now I
thank
request
you.
Dr.
Thank you so
Kuldeep sir.
much.
Yes.
Yeah.
Now I request Dr. Kuldeep sir to start the session. Over to you, sir.
Okay. Let me quickly share the screen. Okay. Uh, Yeah. Are slides visible?
Yes, yes, sir. Screen is visible, but your voice is fumbling.
Okay. Okay. So it is voice is breaking.
Now it's okay, sir.
Okay. So I think if I'm not sure if it is related to internet, then I think
Now
uh,
it's okay.
probably it is
Now
better
it's
to.
now
It
it
is
is
fine,
better, sir.
right? So if it is happening, if there is some interruption during talk, no, please interrupt me so that I'll switch the internet, okay, in between.
Sure, sir.
Okay, yeah. Thank you so much for the invitation and so much for welcome. So today, the broad topic is the performance optimization for high performance computing applications, right? That's a very broad area, and given my little experience in that area, I have chosen one particular work that I did at Oak Ridge National Lab, and I felt that that has very good, intersection with the current, with the today's theme and the today's topic. So the topic that I chose for today's talk is a scalable object detection workflow for remote sensing data, challenges, performance analysis, and deployment. So here, um, so I basically come from geospatial geo AI background, and that's why the specific application is related to object detection workflow using remote sensing data. But the methods and the performance analysis and optimization approach, or the things that I'm going to talk will be more likely general. We can apply to any other applications for any other domain also. So since this work I did while I was at Oak Ridge National Lab, so that's why I thought I'll put my contributor list here. So all these people, they contributed in this work. Although I led that work, but these people, researchers, they contributed in this overall work. So currently I am working as a research scientist at Reliance Industries Limited. Okay, so I so I'll try to. I prepared few slides. I'll try to cover the topic as much as possible, but let's not force feed the entire the number of slides that I prepared within this time window. So I would like to make this talk, rather than as a one-sided presentation. I would like to make it more discussion, more interactive. So please feel free to ping me in between. You can raise your hand, and we can discuss some of the things that some of the questions or the doubts that you have, or any thoughts on a specific thing. I will also in between, I'll pause, take a pause, and then I'll raise questions. We can have some discussions also. So yeah, so let's move ahead. So since this is remote sensing uh, domain, or the remote sensing data, so I thought I'll share some of the information from the big data perspective. So when we call something as a geospatial big data, okay, so it's a big data only, but it has a geospatial nature, meaning the data that we have will have the location information in terms of, say, latitude and longitude. That is the brief definition of the geospatial big data. Now, on this slide, just to give you, just to set up the foundation for today's talk, I'm presenting some of the data sources from where we can gather the geospatial data, and some of the facts, some of the recent facts that give us the uh, information, give us the perspective about the quantum of information that typically we or the organizations or the societies that they generate or collect. And hence the conclusion that I want to make at the end of this slide uh, was why there is such requirement of high performance computing, and where we can actually apply, for what type of application we can apply. So basically, these are the four major data sources on the left side you can see. So one is the Earth observation data. So this Earth observation data is actually typically captured by satellite, uh, which are revolving around the Earth. These are called as the remote sensing satellites. And you can see that NASA currently Earth observation, NASA currently captures all this data. If we just consider only NASA's Earth observation repository, this data was estimated to grow around total Earth observation data was estimated to grow around 250 petabytes by next year. Then there is another category of the data source, which is called as a geospatial information. So typically, that is one of the example of the geospatial and model simulation. So climate simulation means weather and research forecast WRF model. So this type of climate simulation models are actually very compute intensive. So typically, when we run this model, they need the compute. That is one thing, but they generate a lot of data. So as per the sixth IPCC report, International Panel for Climate Change, Intergovernmental Panel for Climate Change, reported the estimated amount of data that will be produced um, by this climate simulation will reach around 100 petabytes. That is only for simulating the data. But then there are further processes. Once you simulate the climate model, it will generate the data. But again, you need to calibrate it. You need to do some post processing. That will add additional amount of data. So that is one scenario. Then the third category is Internet of Things. So this I think we might have heard about it, being from the computer and the IT, domain. So we know that there are a lot of low cost sensor or the edge devices that we call that are being now deployed and they are connected to internet. So as per the IoT analysis analysis by one particular report, it is estimated that by end of the 2024, meaning in this year, the total number of the IoT devices that were connected will reach somewhere around 18.8 billion. So that is another a lot of data, and all those IoT devices are inherently they are located. They have, if they are physically located, they will have the location. So the data that is being generated will be geospatial in nature. And then there is a fourth category of data, which we might be more familiar, which is called as a volunteered geographic information. So one quick example is earlier known as Twitter. Now it is X platform. So basically, when you post some tweet or when you post some Facebook post or something like that on social media, you have an opportunity to tag your location also. So if you tag your tweet, it is called as a geospatial information. So approximately, as of now, approximately it is estimated that over 24 millions of geotag tweets are being generated every day. So that is again a lot of geospatial data. So this is just to give you a perspective that at in one particular domain, which is geospatial geo AI domain, the data that is being generated is humongous, and this is going to be increased, and hence there is a requirement to uh, process that much data. There is a requirement of these high performance computing systems are essential. So I think that sets the ground. If anyone has any, specific query or specific thought that they want to share, please feel free to share. And let me know if you have any question or anything you want to.
Participants, if you have any question, please feel free to ask, or you can post your question in chat box also.
Yeah. Okay. Yeah. So I'll proceed, but feel free to interrupt me in between. The work that I'm going to present today, or rather discuss with you, was presented in this or published in this journal paper. This journal paper is actually from the journal name. I'm not sure if yeah, it is performance optimization and something along those lines. The name of the journal. Concurrency and computation practice and experiences. So basically, concurrency means computing something in parallel, and what are the different practices that we typically adopt or typically do when we do high performance computing or when we do any computing operation, and what are the experiences that we gain. So that was the journal theme of the journal. And the work that we did for performance analysis and optimization for scalable deployment of deep learning models for country scale settlement mapping. So I'll go through this. I'll give you a brief of this application so that you will get the idea of okay. So just to give you a motivation, now consider this scenario. So basically, um, let's look at this scenario. If a government organization wants an approximate count of a vaccine X for a country Y, where the updated population data is not available. Okay, so this is the problem statement. This project that we did was for Gates Foundation, Bill Gates and Melinda Foundation, and they had this specific problem statement. Maybe they wanted to, ship some particular vaccine to some other country, specific country in the Africa, and they seems to not having any population related census information or population data. So that was the problem. And being from the geospatial background, the natural solution came that we adopted was using remote sensing images. Uh, can we at least estimate the population of the country? So remote sensing imagery is the only information that was available to us at that time. Uh, so the method that we adopted, I'm going to discuss about that. But is this motivation or the problem statement clear? Are there any doubts, or do you have any thoughts on how we can approach the problem, as opposed to the way, or what could be the approaches that we can think about in case we don't have, say, population information or the data that is not available, census data that is not available. So please feel free to jump in. I'll be talking about one specific approach that we took from the remote sensing domain. Yes, I think, yeah, someone has raised the, yeah, please feel free to, yeah.
Hello, good evening, sir. I want to say something regarding if we don't know the population and if we want
Right.
to understand. So we can go back into the history like interpolation and extrapolation that we generally use in stats to calculate how much vaccine or how much population is going to increase in
Hmm.
near future or something like that. Yeah.
Correct. So basically, we assume that we have the historical data available, right? Some information from the history that is available, and then we'll do some sort of extrapolation using some statistical approach, right? So that is something. I mean, that is correct approach. With, of course, we need to make some assumptions and apply some statistical method on top of it. So it this particular approach or the similar approaches, they fall under a method called population density estimation. Population dynamics is a estimating population, is another different field, and they in that field typically we tend to develop or build statistical model for population density. So that is one thing. But this population density estimation approach, as you mentioned, or some other approaches, similar approaches, they tend to have some sort of assumption about availability of the some information from the history, or maybe availability of the nature of the statistical distribution, Gaussian distribution, or something. So those kind of assumption needs to be made. So that is one that is one type of modeling that people tend to do. uh, so now what we did here was, since we have the most updated data available, historical data of course we can use, But now, in terms of remote sensing data or the remote sensing images, we can actually see the building rooftops or the geometry of the building. So that is the most updated data that we have. So the task here was to first identify the pixels from the remote sensing image, which are basically, which are actually a type of, say, buildings, which are basically type of settlements where population can stay or population live. So those, that was the first task, to identify the pixels, and then there are some post-processing steps that might be done on top of that output. Once we know which particular pixels belongs to settlement, which are the potential pixels where the population can stay or live. Once we know that for a given area, then some sort of density estimation or those kind of approaches can be used, which can be used as a typical input for this population distribution model, where you can again include the historical information, and at the output you will have some estimation about the population. So that's what I understood when I worked on this project. Although we were concerned only about the first half of it, where we have the satellite data, and then we try to, classify the pixels on the satellite images, that may look like the satellite a settlement, where either they are a part of building, residential building, commercial building, or whatever. So we want to just identify those. And the second part was, of course, the population density model that we can train on top of the different inputs and the assumptions that we have. So yeah, I mean, based on the question, I sort of understood that you got the, motivation and the problem statement. Is there any other question? I see one more hand raised.
Yes, Abira ma'am, you have any question?
I think she's on mute.
Uh, just a minute, sir. Abira ma'am, you can unmute and ask your question. I think by mistake she has raised her hand. Is it?
Yeah, no problem. I think yeah, over the talk, maybe yeah, we
Yes.
can discuss. Hmm.
Yes.
Okay, so I assume that the motivation is clear, and okay, so this is just to give you an example. On the right side, this is the satellite imagery. It is not the colored imagery because I'm showing one particular band from that image, and these highlighted pixels, they are the pixels that belongs to the settlement object. So those object could be residential building or some other individual houses or something else. So this is just to give you a visual, and just to give you an idea that I have some numbers in further in slides, but just to give you an idea, this typical satellite image was of the, or size of this image was of the order of 40,000 pixels cross 40,000 pixels. So that is the dimension of the image that we are talking about here. And you need to process this entire image. Uh, just only one image. There are several thousands of images that we need to process if you want to process that country, that specific country that we worked on. So that much big amount of data that we are talking about here. And again, that justifies why we need high performance computing sort of systems. Yeah, again here I'm mentioning same point, that the important input to various population distribution models could be the the uh, output of this particular process, that processing high resolution remote sensing images, and then try to find the settlement information from those images. Okay, and then some other information, like, so during last few years, there are many satellite platforms that are available, and due to the improvement in the sensor technology, now we satellites are able to capture data in high spatial as well as spectral resolution. So by means of spatial mean, one particular pixel of the satellite image captures what uh, space on the ground. So typically high resolution images, one pixel captures 100 centimeter by 100 centimeter sort of area on the ground. So that much high spatial resolution information that we are talking about. I mean, we typically see the Google Earth image or Google image satellite images. So we know that we can see the rooftop, building rooftop. So that was because the high advancement in the satellite, sensor technology, and that inherently that development in the sensor technology led to capture the high resolution data, which basically led to generate more data, more remote sensing data. And again, due to the increase in the satellite technology, satellites are now able to increase their revisit period. Revisit period means at what particular frequency, after how many hours satellite will revisit the same location of the earth. So that also increase, so which again in turn generate more data. So because of all those development, there are new opportunities to understand our earth features basically at more finer spatial scale. But that led to challenge also. Uh, the more data that we have, we need to have more computing resources to process the data. So that's what I'm trying to say here. So crunching billions of pixels. So mapping for our particular task where we are trying to map the human settlement at a country scale from a high resolution satellite imagery is a challenging task. And since it requires to process billions of pixels, and in terms of critical events such as flood disaster or something earthquake or some other forest fire type of disasters, we need to those events are time critical events, and hence those many number of pixels need to be processed in a limited time. So that again make the situation worse. So we need to have high performance computing system to process this much data. So what we did for our work was we used a leadership class supercomputing facilities that were available at Oak Ridge National Lab. So I'll give you a glimpse of what I meant by this supercomputing facility. But before that, I think I'll briefly tell you. I must tell you the how this end-to-end deep learning-based human settlement mapping workflow looks like. So this will I will not mostly talk about deep learning aspect of this work, because most of us I think are now working on this particular area. So it is sort of very much similar to what we typically do in computer vision. But what we are interested in this particular context is from the high performance computing perspective. If you want to perform this particular task, what could be the how the workflow looks like, and what could be the characteristics of that workflow that we expect. So these are the four typical characteristics that I pointed out here. There may be others, but the workflow for this object detection approach, that workflow should be scalable in nature. Okay, so when we say scalable, we mean that whether you are working for whether your workflow, that object detection workflow, must be can be used for at the city level data. At the same time, it can also be used at the country level data. So when you move from a city level sort of information, processing city level information, and when you go from city level to country level data, you don't need to do any sort of upgradation to your workflow. It has to be the natural shift. It has to be scalable in that sense. So that's what I meant by scalable. Then the second characteristic is it should be fault tolerant. So today's topic mostly will revolve around this particular characteristics, fault tolerance. So fault tolerant means this when you use any kind of HPC resources, it is shared resources. If it is hosted in your college, if it is hosted at some organization like Oak Ridge National Lab, which is maintained by lab, so those are the shared resources, and any failure can happen while your job is running on those systems. But suppose your job is 50% done and something happened, you don't want to, of course, you need to finish the rest of the 50% processing. But when you resubmit your job, when you rerun your job, you don't want to, repeat the first 50% of your work. It is already being done, right? So you don't need to, repeat that. You need to resume your work from the 51st percent, meaning after the first half has done, whatever data was there, it was there. You no need to reprocess it again. You need to resume it from where that work was failed or that process was failed. So it has to be, it must be done in the seamless fashion. So that's what the meaning of the fault tolerance. So if something happened, your workflow should be self-sustainable. It should sustain against those kind of failures, and it is able to resume the task from the last failure point. So that was I meant by fault tolerant, and we'll be able to talk more about it. Then the optimal resource utilization. So here I specifically mention about GPU resources because we use GPU resources, and that was one of the target that we had, that whatever GPU resources we have, we need to use them optimally, uh, or whatever resources for that matter that we are going to use, it needs to be utilized optimally. Then deployed on supercomputer. So basically, our main task was to develop this workflow, and this workflow we wanted to run it on the Titan supercomputer. So these were the characteristics of the workflow that we initially thought about. There were many other characteristics, but these were the major characteristics that we built our workflow around. Um, since I talked about these Titan supercomputers, so let me show you how that supercomputing facility looks like. So that will give you the broader picture. So this is how the supercomputer looks like. It basically, I don't have the exact square feet or square meter area, uh, but it was a big ground floor that was occupied by this entire Titan supercomputing facility. Uh, but let me and in it was basically made operational in year 2011 or 2012, where that time it was the first supercomputer, fastest supercomputer on earth, and it was decommissioned in August 29. I was actually present there when they actually switch off this entire machine. So that was really different experience that I had. Now this Titan supercomputer, as you see, it looks like a cupboard. It's a collection of cupboards, the typical cupboard that we have at our home, right? Two-door cupboards. So those are the collection of cupboards. We call it as a cabinets. So there are there were total 200 cabinets. You see, it's a collection of 200 cabinets. Each cabinet will have some trays or the racks. Rack is sort of equivalent to the CPU that we have in a typical desktop system. So it has a motherboard, RAM, processor, and all other necessary things, internet connections and all. But it doesn't have the screen. It's just a rack. So it is found as a rack. So basically, there are total uh, 200 cabinets, and each cabinet will compose of some of the racks. Now altogether, if you just calculate the those number of racks or the nodes, basically, so we typically call it as node. So there are total 18,688 nodes or the racks were there. And if you just look at one particular node or one particular cabinet, it had 16 cores. So this whatever processor that it had a 16 core processor and one GPU. Okay, so one GPU was from NVIDIA K20, basically GPU card was there. So altogether, if you see, there were total 18,600. So that was a huge computation power that was available in place. So that is how the supercomputing computer looks like. Now this and again, I think total number of CPU cores, if you see, these are in the order of 300,000. So that is the huge amount of power it has. But it is a shared resource system. So basically, if you have something some application is running and you want to process that. So you need to write a proposal. They will allocate some typical core hours basically to be used on this computer, on this supercomputer for a given duration of say one year or so. And it is being shared among different researchers, different organization, universities, and uh, it's sort of a shared resource. That's what I wanted to make the point. Now, this particular compute resource is broadly divided into three parts, which I will which I will describe here actually. But I think this particular slide will give you the idea of how the supercomputing type HPC system looks like. Now, just to give you a small illustration of how we use that HPC system. So typically, these systems are, worked around job scheduling. So whatever you want to do, whatever processing you want to do, you need to create a job submission script or job script that we typically call. So this entire system, supercomputing system, is broadly divided into login nodes. So whatever nodes that we have, you have the compute nodes, then some of the cabinets or the nodes, they are dedicated as a login node. So first, those login nodes are actually connected to the external internet, and these compute nodes are not available to be accessed from the outside. So you need to first log in into the login node, and once the login is done successfully, you need to basically then formulate your job script. So whatever Python script or training script or executable that you have, you need to put it somewhere onto the storage that is also available. So some of the nodes are also storage nodes basically. You need to put that there, and then in the job script you put the location of the scripts and all typically, and then you submit that script to the job queue basically. So there are some schedulers available, scheduler software basically, tools that are being used in this high performance computing system, which basically keep all the job scripts into the queue. And then you typically this job scheduler, based on some scheduling policy, it will assign the job to the dedicated available compute nodes, let's put it that way. So whichever compute nodes are free, the jobs will be assigned to them. Now there are some other things like how many compute nodes you are asking for what amount of time you want to access those compute nodes. Those other factors will be taken into account while deciding the priority of your job script. So that is the flow of how we typically execute the job. Now on the right side, you see that there are total 8 or 9 jobs that I'm showing, and you can see that there are 6 nodes. And say for example, job 1 needs only one node basically, so it was assigned to node 1, while job 2 parallelly was assigned to, after some time, was assigned to node 2, 3, and 4, because job 2 might be needing three nodes into the system. And this is how it looks like when you typically, multiple users typically submit the job onto the supercomputer. So I hope the picture of how the supercomputing, the shared facility of supercomputer looks like, and how typically the job scheduling is being done. So I'll take a pause here for a second, and please let me know if you have any, thoughts or any questions or any doubts about the motivation of the settlement mapping work and the characteristics of the object detection workflow that we use, how the supercomputing facility looks like, any specific doubt about it.
Participants, you can unmute and ask your queries or question. Sir,
Okay.
there are no
Uh,
queries. You can go ahead.
yeah, yeah. So, so that was what so far what we have seen. I basically set up the foundation of how the big data looks like in specifically in geospatial domain, and I provided the problem statement that we worked on, and then the computing facility that we have used. So from the beginning, through the motivation and the supercomputing facility that we use to basically address that problem and solve that problem, to deploy the workflow that we built. Now let me jump onto the next aspect. So this is all good, but when work on this type of big problem, specifically on this type of when you use this type of shared resources, computing resources, these were the typical challenges that we face. Some of these, so I have listed here four challenges which were specific to the uh, HPC system that we used, which was the Titan supercomputer. But those are more or less same problems, and mm, throughout this work, we try to address those problems. So that's what I'll be discussing. So the first problem is preventing data loss due to runtime failures. I think I briefly touched upon this particular part. So you don't want uh, failures are not in our control actually, correct? What we can do is, we while processing the data, we somehow bring in some mechanism so that the data won't be lost. Whatever 50% data that you have processed will be secured. So that is the first challenge that we need to address. We need to every time when we have this when we have to use this HPC system which is shared, and when you want to do the computation for large data, we need to make sure that data loss, because that job won't be finished in say 5 minutes or 10 minutes of time. It will be running for several hours, sometimes for several days also. So you don't want to lose the data, the process data. So in our case, the process data was actually, if you guess, it was the settlement map. Meaning, given a satellite image, if you just create a grid of, say, blank grid of matrix of 40,000 by 40,000, you want to know that which pixels belong to settlement and which does not. So basically, it's a binary map, I would say. And as you process the image, you basically tend to fill those matrix. So at any given point while processing, that matrix is partially filled, and that is something that we need to preserve. So that was the in our context, that was the data that we wanted to preserve. For your application, for any other application, that data might be different, or the data that you want to preserve, that nature of the data might be different. uh, it depends on the problem, but in general, you don't want to lose the data. Then second is the resource utilization and the long tail effect, basically. So resource utilization, as name suggests, meaning, suppose you are asking for say 5 nodes, and 5 nodes, each node come up with one GPU. So these are the costly, time consuming. These are the costly resources basically. And when you process the data on these resources, you need to make sure that these resources were utilized fully. It shouldn't happen that one particular GPU was idle for long, and one and three other GPUs or four other GPUs were only processing the data. That shouldn't happen. So the distribution of the work, or the distribution of the data for the process that you're going to run on each of this node or each of the GPU, the distribution of the data must be fairly uniform, so that all the GPUs or the computing resources will be busy, and that way it will achieve, to some extent, it will achieve parallelism, data level parallelism. So that was what I meant by resource utilization. And then the long tail effect. So the example which I gave you, let's take a same example. Suppose you have 6 GPU nodes, and the data distribution was such that one of the GPU was, let's assume that three of the GPUs finished the processing of the data within 1 hour. Okay, and the remaining one GPU basically kept processing data for another 1 hour, basically. So if you just plot the task duration, basically, um, uh, so it will give you this type of graph. So what it shows that, for few of the processes or the GPU or the resources, they finished early. That's why their duration was less. But there were some of the resources which kept processing your task for the data with the data that you assign to those tasks for longer hours or for longer time, and that will give you this type of long tail kind of distribution. So that effect is not good actually, because what you're doing here is, uh, you're saying that in this region, four processes were basically finished the processing within 1 hour, but for next 1 hour, all those four resources were actually idle. Agreed. So that was, and because of that, those resources which were idle were we loosely we can say that they were wasted, and that was not a very good policy of the data distribution. So that is something that we need to take care. And then the constraint proposed by Titan's job scheduling policy. So that I think I'll talk about in the next subsequent slide. So when you use the shared resources, you need to take care of, scheduling policy. So I told you about scheduler, right? So scheduler typically has first in first out, last in last out, or LIFO, those kind of policies. More complex policies, I should say. Those are the very simple examples. But then, because of the shared nature, this supercomputer must give equal opportunity to all type of users. It should not be like that. If a user has requirement of only one node, as opposed to some user may have requirement of say 100 nodes. So based on the nature of the job, it should not starve the first user, because it has limited requirement of the resources versus 100 nodes of the second user. It should not prioritize the second user over the first user just because it is asking that user is asking for more number of nodes. So because of that, uh, to maintain the fairness, there has to be a scheduling policy. Most of these large supercomputing systems, shared system, they have the scheduling policy in place. And then tuning to the resources that you have. So at that time we had, so the work that we did was in 2019, 2020 time frame, and the GPUs were installed. They were developed in 2010, 2011 actually. Those were the latest GPU at that time when the Titan was installed. So K20 were actually new GPU, but by the time we used it, those GPU become legacy GPUs. So by meaning that, just to give you an example, the RAM was very small, meaning less than 4 GB or 4 GB, something. I do not recall exactly. But the thing was, we were not able to fit the entire satellite image onto the GPU memory. So those are the specific challenges that we wanted to address. And these type of challenges may occur even if you are like accessing any medium scale or small scale HPC system, because typically we tend to install the HPC system, and then its lifetime, if its lifespan is more than 5 years or 6 years. So by the time when you use down the line 5 years, 5 years down the line, 6 years down the line, that time the resources might become old or the legacy. So we need to take care of those kind of challenges also. So those are the typical challenges that we pointed out for this particular work. Okay, so yeah, are there any specific doubts or anything? uh, so i- to i- so in the next few slides, we'll be discussing more about the second point, or rather this first 2 points actually. How we address the problem of preventing data loss while running the job, and then how we addressed the fair resource utilization challenge, and then how we avoided the long tail effect to some extent. So those are the two specific challenges that we worked on. Okay, so we'll be talking about it. So about these two challenges, please feel free to jump in if you have any doubts. So again, this is the scalable object detection workflow, but I think I have given you the brief. I'll just summarize it. So end to end, this workflow has 4 stages or 4 phases. So in phase one, you acquire the image. It is a image acquisition. So wherever that images are hosted, you need to first acquire it from that place to the Titan supercomputer's premise, or you need to copy, you need to host that data into the storage of the Titan supercomputer. So that is one thing. So most of the time these data provided agencies are different, so we need to copy that data. So that is the first stage. Second stage is image pre-processing. So basically, just to give you a very simple example, I in the previous slide I mentioned that the GPU RAM capacity was limited, say 4 GB or something like that, and say your satellite image is about 20 GB, and you want to like put that entire image into the GPU, it is not possible. So you need to have some strategy to tile that image into the manageable chunks, or the size of the image, so that you can put at least partial or some part of that image, entire image, into the GPU, process it, get the output back, then put the next chunk of the data to the GPU. So that sort of you know pre-processing for that particular thing, we need to have some pre-processing in place. So that is something is being happened in the second stage. Third stage is mostly it revolves around the model training, which we already know, and I'm not going to touch that CNN training part of it. That is being happened here. And once your model is trained, now your task is to deploy that trained model on several nodes of Titan supercomputer along with the data. So we need to distribute the data among different nodes, and each node will get different instance of the trained CNN model, and then independently they will process the data. So that is being happened in the model execution or the inference phase. So that is the fourth phase. It is sort of very general, standard uh, workflow that one can think of. Again, I think I'll skip this part, but this is because this is a very, very general, very naive CNN sort of model that we use at that time. That time we were also learning, and it was a new thing for us. So we used very simple model, CNN model architecture. One point that I would like to highlight was the model architecture that we use, the backbone architecture, takes input image of this particular size, so 144 cross 144. I don't exactly recall why we made that choice, but the important point was the overall satellite image size is of order of 40,000 cross 40,000, for example, but individual unit that is being processed on the CNN by the CNN model is of size this. So you need to have some mechanism in place at this second stage where you chop the image into the manageable size. That is being done at this particular stage too. Okay, so this is the model development phase. Now, quickly I'll tell you about a system called NVIDIA DGX1. So basically, since this is about the model development or model training, so the system that we used to train the model was called as a NVIDIA DGX. So this is how the architecture looks like. So this NVIDIA DGX is again looks like this. It's also a rack kind of thing. It's a CPU, standalone CPU. It has a standalone, the system that we have with motherboard and CPU. So it has two CPUs, CPU 0, CPU 1, and then it has total 8 GPUs. So four GPUs were actually more closely connected to the CPU 0, and then 4 GPUs are CPU 1. And then all the GPUs are actually connected to each other through a fast interconnect called NVLink, NVIDIA link. Uh, the main point was these GPUs were Tesla V100, which was the cutting edge GPUs were available during 2019-2020 timeframe. Um, so the models that we trained, those were trained on this cutting edge GPU technology. But the model that we are, but those trained model which we are going to deploy on the Titan supercomputer, they were actually deployed on the legacy GPUs, which are K20. Like they were like almost 8 to 9 years old, older than the this DGX GPUs. So that is again one sort of discrepancy that we had. Uh, Not challenge, I would say, but I think it was a discrepancy in the model. So basically, we had to do some uh, because this was the advanced system. Uh, we were able to fit more number of images onto the system. Maybe we were able to process larger image size also. I don't know, but when we apply use these models for the during inference, we need to make sure that that is being compatible with the legacy GPUs. So that was the point that I wanted to make. Okay. Again, these are the very uh, intuitive phases that or the steps that we particularly do during model inference. So I shown you the entire end-to-end workflow, then what model architecture that we use typically, what system we used for training the model, and now in the last phase, fourth phase, where we actually use that model for inference. So these are the few steps. I think I briefly touched upon it that that there are some, say you need to process, you have 10 images, satellite images of covering some area of the country, and now you have a model which was also trained, which is ready for the inference. So what typically we do, we typically reserve 10 nodes on a given HPC platform, and then you typically assign one image to one node, and then for each node or the process that is being run on each node will basically invoke or initiate the independent copy of the trained model. Basically, you need to initialize that model with the weights, trained weights, and that is independent from the process that is being run on, say, node 2. So both are the independent. So it is sort of a embarrassingly parallel kind of the architecture. And here we typically use the MPI processes, message passing interface kind of mechanism, to distribute the data and distribute the data among the nodes. Yeah, so basically build the model. So this again, please don't go behind the terminology that I used here. What I mean is we instantiate the model. So typically you know is instantiate the CNN model and initialize the weights. So that is what I meant by build the model, and then you perform the prediction. So prediction has all these other stages, which are again pretty common. But once the prediction is done, it will write the output map, which I already described to you how that output map will look like. It is typically binary map. Typically, it has a probability value. So instead of directly saying 1 or 0, we can say that it's a probability values of a pixel being settlement. So that's the output map that we write. So that's how, in broad sense, the model execution phase looks like. Okay. So now I'll shift the gear a little bit, and then I'll talk something about load balancing strategy. Then we'll circle back and try to see how this load balancing, how the importance, why this load balancing is important, and how it is uh, related to these first two challenges: resource utilization, long tail effect, and to some extent preventing data loss. So the resource, as I already mentioned, that we use the remote sensing imagery of a country called Zambia, and its overall area was close to 680,000 kilometers square. Uh, the satellite images that we used were captured by Worldview 3 satellite. The total size of entire data, which comprised of 5426 images, were 13 TB. So that was the data. On the right side, I'm showing the image size, a histogram of the image sizes versus the count, basically image size versus the count. So you can see that most of the image sizes were located somewhere in this region, somewhere around say 20 GB to say no, 2.2 GB to say, for example, 2.9 GB or 2.8 GB. But the workload that I highlighted in these red circles on the left side, that capture the small size images, and on the right side that capture the large size images. So basically, you can see that there is a disparity in the size of the data that you use. So this is because the way we got the data. Now, uh, it depends on, again, because since it was a remote sensing imagery, we cannot guarantee that we always get the data of the same size. It again depends on the processing that was being done at the data production size. Once the images was captured, it had to go through a lot of pre-processing, post-processing, and then it will they basically crop the images of the manageable size and so on. So something was there, but because of that, the data that we got had this, disparity in the sizes. So you can see that this was the imbalance, an example of the imbalanced workload. Now, here is a question. So if we assign whatever number of images that we have, if we just allocate 5426 nodes on the Titan supercomputer. And for each node, suppose in naive sense, if we assign one image to each node and ask to process, and we submit that entire thing as one single job, what will happen? So let's think about it and let's try to, connect that with the long tail effect. So basically, the there are two extremes, two extremes, and there was some load which was of fairly similar size. So one was the small size images, one load was the large size image. Now what will happen? The small size images which were of say less than 1 GB of size, those images might be processed within. I think some disturbance is.
Yes, yes, yes.
Arki ma'am, please unmute yourself. Mute yourself.
Okay, okay. Yeah. So now let's try to imagine if we submit that entire task as one single job, right? So what will happen that some of the processes which were running on the nodes, which got images of say less than 1 GB of size, they might finish within this particular region. But some of the images which were say above 4 GB of sizes, although they are very small in numbers, as we saw on the histogram, but they will finish somewhere in this particular region, right? And as an effect, we will get this type of uh, long tail long tail kind of graph if you try to plot the task duration versus the total number of processes that were finished during that particular task duration, if you plot the histogram. So again, that was because that uh, since our workload was imbalanced, there were two reasons. One, our workload was imbalanced, and then we assigned the entire job as entire task as one single job. So those were the two important reasons. So now what we can do? So what we can do? We can partition the entire workload such a way that the images of similar sizes might uh, come together, or they might be grouped as a sub workload basically. And when you do those kind of partition, you can use any sort of approach. So here I am showing another visualization of the same information. So here I am just plotting the histogram of the image size in terms of GB, but here I'm plotting number of rows and number of columns of a given image, and this is how the workload looks like. So again, you can see that it's not very well distributed across number of rows and number of columns. It is most of the images have the number of columns which fall within the same row, but it has a number of rows which are from 5,000 the way we received it, and because of that, it created the imbalanced nature. So what we did the workload partitioning. Uh, this is again very general term. So basically, based on the type of the data that you have, you can have your approach to partition the data. But the underlying thing is very same, that if your workload is imbalanced, we need to make it balanced. So we use some kind of clustering approach, something to basically partition our data based on the number of rows and number of columns. Very simple approach. And that's how we divided our entire workload into 6 particular jobs, as opposed to one single particular workload or one single job. So you can see that this job 0 has number of rows and number of columns in the range of say 35 30,000 to 40,000 columns, and say 5,000 to 10,000 of rows. And similarly for other. Uh, Interestingly, the job file images which are of the right side of the workload in that graph, uh, they have very distinct group which is different than this. So again, it is highlighted separately. Uh, and for each of this group, we have separate, jobs. Now, once we have this job, so what we did, we addressed one thing, that we don't want to, submit the entire workload as one particular job. We segregated it into different partitions, and then based on some criteria, and then for each of the partition, we have independent job. Now, this job file is no more dependent on the job execution of the job flow, or rather job zero. So job zero might, you might have guessed that job zero might finish early, and job five might, finish little bit later. But during that process, you are not going to hold the resources that were assigned for job zero. So that was something that we achieved during this process, which was difficult when we, assign the entire workload as one single job. So was that, argument clear? Uh, I think it is very simple to understand, but it is very important to uh, make sure that your load is balanced among your processing units. That was the highlighting point. And for that, we can use any other approach. The nature of the data was such that it was image data, and for us, it was slightly very easiest way was to just check number of rows and number of columns, and based on that, just group the data into different partitions. But we can have some more complex strategy also, based on the image characteristics or the information content in the image. It may happen that one particular image, even if it is a big size, it might cover a desert region. But in any other image of that country might contain complex buildings, structures, and all. So even though that second image is of smaller size, it might take a little bit more time for CNN to process that complex information, as opposed to the image which covers the deserted region. So those kind of complex rules can be come up with based on the. So just to illustrate the dimensionality and the size of the data, here I am just showing you the. I sampled two images from each of this workload, and here you can see that for cluster zero, the number of rows and number of columns were of 34,000 cross 6,000, and the size was somewhere around 500 MB or half a GB, versus images in the cluster 5, where the number of rows and number of columns were of 40,000 cross 46,000, and the image size was of the order of 3.6 GB. So basically, I just took two sample example images, data points from each of those cluster to illustrate the size of the data and so on. So now the next thing is, now we know that we had the image list or the list of the data. In the second stage, we group or partition the data, and then we created this independent lists. Now, since the lists are independent, or the data, each partition is independent, we can create the different independent jobs that will take care of execution of that all the images that belongs to that particular partition. Correct. So that is something being happened here, and more complex thing will happen at the job submitter model. So basically, the one thing that we tried to address at this particular stage was, we wanted to make the workload balance, and once the workload is partitioned into sub partitions, we can create independent jobs, and those jobs will be submitted through this job submitter script. Now we are approaching towards the final part of this talk, where we will discuss a little bit more about the job submitter. So if you remember, there were two challenges. One challenge was to runtime failure. We want to avoid the runtime failures. Specifically, we want to avoid data loss due to runtime failures. That was one point. Second point was, we want to make sure that the resources are utilized near optimally. So through this workload partition, we tried to address the second point, that we wanted to make the resource utilization as optimal as possible. Now, uh, the first point which was still remaining, how we can make sure that our data is not lost. Meaning, in a more technical way, we can say that how we can make sure that our workflow is fault tolerant, basically. So that is something that we are going to discuss. So before doing that, I will just give you one example which I told you earlier about the Titan's job scheduling policy. So each of these computing resources or HPC environment which are shared, they tend to have the job scheduling policy. So one example is this Titan supercomputing policy, and this policy is based on two specific aspects. One is for how many number of nodes you are asking for to execute your job, and for what duration you are asking those computing nodes. So suppose, let's take an example of this bin number 4. So there are 5 bins. In bin number 4, meaning if your job asks for say 140 nodes, let's say 140 nodes, which belongs to minimum of 126 and 312 max nodes in that particular bucket. And if you are asking, if your requirement or ask for computing nodes belongs to this particular bin, then for maximum 6 hours you can access those 140 nodes. That's the meaning of this particular bin. You cannot run your job more than or post 6 hours. So it is very difficult to make sure that your job will finish within 6 hours. Maybe it will take more time. Okay, so what will happen if your job has finished say 80% of the data, but you have hit the wall time, basically 6 hours of wall time. You might need say 2 more hours to finish the rest of the data. What will happen? So that is the situation will arise due to the which is very specific to the scheduling policy. So for different HPC system, these policies might be different. So we need to make sure that our workflow, or very specifically this job submitter script which you write, will take into account this scheduling policy also. Now, how we can do that? That is something that we'll discuss. So now I have given you idea of what are all things that can happen. So when your job runs during that runtime, either it will finish successfully. That is number one very good scenario. Then second scenario is some failure will happen. Either it could be because of GPU failure, node failure, or network failure. That failure might happen, and your job will get terminated. That is second scenario which we want to avoid. And the third job termination may happen because of the exceeded wall time, which is because of the scheduling policy, which I described just now. So those are the three specific scenarios may happen, and your job submission script that you have must take into account, or some sort must take into account through some mechanism. It should take into account all these three scenarios. So there is a we must have heard about this term called checkpoint restart, basically. So to make our workflow fault tolerant, we are using. So basically, Mr. Rahul is asking that what is the benefit of Titan's job scheduling policy? So one specific so there is one particular point was that Titan supercomputer is a shared resource, correct? Um so if you have one particular user which is asking for say one node, versus there is another user which is asking for say 4,000 nodes or something like that of that order. Um so only based on number of nodes that were being asked, should we prioritize this second user more, prioritize the second user over this first user, or should we, since the first user is asking only for one node, we just assign that job before the second job so that it will be finished earlier and that one node will be released. So what is the trade-off? So this particular job scheduling policy will make sure that this entire supercomputer will be shared among all the categories of user fairly, uh, So it's about the fairness of the computing resources. How fair your scheduling is. Any user must not be uh, starved from accessing the computing resources. So that was the intention behind it. But I'm not sure actually how they came up with this particular policy. But the intention was that these resources must be shared as fair as possible, as fairly as possible. Okay, so I think I made that point. So yeah, so what I was telling was the checkpoint restart strategy, right? To make we might have heard about this particular term in processor microcontroller systems, specifically in operating system, basically, where our operating system try to avoid the data loss by maintaining its own restart strategy. Most of the database system, they will have the checkpoint restart strategy, so on. So what we typically do is we try to log the some amount of information so that when in the event of job failure or the runtime failure, when you resume the job, you need not start from the beginning. You can resume the job from the point where the job was failed earlier. So that was the logic. Okay, so I hope we understand the meaning of checkpoint. It is, in a simple sense, it is a log that we want to write. So in our case, it's a partial binary map that we want to, write into the persistent memory, persistent storage, so that at least whatever data was processed was available into the persistent storage. So that we wanted to make sure. Yeah, same thing I mentioned. Now, this checkpoint interval. So I'll talk about this checkpoint interval and some of the points that I wanted to make about the optimal checkpoint interval. And I'll show you the graph, one scenario, which will give you the idea, which will sort of summarize the entire fault tolerance of the workflow that we tried to make. And then we will conclude. So we are now moving towards the final few slides of the today's talk. So since we are talking about the checkpointing, so in checkpointing, basically, we want to save the intermediate output. That now we understood. Okay, but the very next question is at what interval you want to log the checkpoint, or at what interval you want to write your data at the persistent storage. Since our say let's say your job will be running for 6 hours, so should you write the checkpoint at every hour, or should you write the checkpoint at every 10 minutes? That's the question, right? And the artifact of the decision that we make are these. So if you write the checkpoint, let's say we represent this triangle, checkpoint by triangle, and this is a timeline by arrow. So if you write the checkpoint very frequently, so likewise, it will slows down the job. Why do you think that it will slow down the job? Let's think about it. Then the second point is, if you take the checkpoint sparsely, uh, then what will happen? Then there is a high risk of data loss due to the failure. For example, you took the checkpoint here, you process the data for few hours, but just before the next checkpoint, the job was terminated because of some failure. So this much job was lost. This much data that was produced was lost. Time was lost, and so on. So uh, what is the trade-off? So I said that if you take the uh, checkpoint very frequently, it will slows down the process. Why will it slow down the process? That was the question that I asked. Uh, so if you remember that Titan supercomputer ka setup, uh, there is that entire facility is divided into three parts actually: compute node, login node, and the storage node. So basically, although the storage nodes they sit somewhere near, but the data, while writing the data has to travel through the network from the compute node, because compute node doesn't have the persistent memory like hard drive or something like that. That data has to travel through the network, over the network, and then it is being returned onto the persistent storage. So that network is also shared. It's not like your compute node has a independent network. That network is also shared, and it is shared among all the other jobs that are being run. So that will definitely add the data transfer time, and then post data transfer, there will be data writing time. So basically, those things are involved. It is not like your storage is very much near to the processing system, as in your desktops or the laptops. So that's why if you take the checkpoint too frequently, your process will be busy more in writing the checkpoint and waiting for data to be transferred from processor to the storage, then processing the this thing. So, and then the downside of another extreme is if you take checkpoint too sparsely, there is a high risk of data loss. So how can we come up with the optimal checkpoint interval? What is the trade-off? So that's where this particular paper work by Daly 2006 came into picture. Uh, so this paper specifically talked about the optimal checkpoint interval. So I'll explain about this, and then we will move to the the final part where I will explain the this particular graph. So if you see that this optimal checkpoint interval, this T optimal, is actually a function of uh, there are two specific terms, which is delta and which is M. So delta is the time to save the checkpoint. So I gave you, I just now I explained that data has to transfer over the network and then to be written on the storage. So what is the total time it will take at the from the point when the checkpoint was generated to the point when the checkpoint was written successfully onto the storage. So that time is called as a delta. That delta you need to capture through the runtime. So basically, you write first checkpoint and you then try to capture the time. Then you write second checkpoint after some time, you try to capture the point. Then you write the third checkpoint. Likewise, you do two, three times, and then you will take the average. So that will give you sort of an idea that, okay, for initial first half an hour, you will get a judgment computationally that at this particular time, based on the the workload on the entire supercomputer and the network, this is the approximate time it is taking to write the checkpoint for this particular job, for this particular image that I'm going to process. So that time you will use, and then you will put it into this formula. And this M is actually the mean time between failures. So this M value is actually specific to the HPC computing facility. So this M is actually very much specific to the Titan supercomputing. So as name suggests, it is the average time between two historical failures that was recorded into the facilities log. So once the system is up, that system is run for several months, 2 3 months, that is called as a warm-up period, sort of warm-up period, and then it was being tested rigorously for next few months. So throughout that entire process, they will basically record the logs. Okay, and through that logs, when you have multiple failure information, you can calculate between two different failures what was the average time. So that was the mean time to failure. When you put these two values into this formula, you will get the optimal checkpoint interval that you can use for that particular process on that particular node. So this T optimum is also different for different processes that you created for different job partitions. Like if you remember, there were 6 job partitions that we created, right? So based on the data that you are writing, at what particular time you are writing, this T optimum is different. Okay, so now we will come back to this job submitter. So basically, this job submitter will uh, query the very important part of the job submitter is it will query the scheduler. So there are several commands that you can use to basically query the scheduler command through command line. Uh, and once the job is submitted, it will create the unique ID. So you can get the log from the scheduler about your job, and you will at particular interval the job submitter script will basically poke the scheduler and ask about the status of the job, whether the job has finished, whether job has not finished, whether if it is finished, then whether the job was finished or terminated successfully. If it is terminated successfully, that means your log was saved and no need to worry about, your job was done. But if that job status was termination, or it was saved as terminated in the scheduler's log, then job submitter script should make a check uh, throughout using the log that you have written, and try to understand whether that job was, even though it was terminated, but was that successful termination. uh, that termination might be because of runtime failures, or that was might be because of uh, you know finishing finishing the or hitting the maximum wall time limit due to the Titan's scheduling policy. So those checks needs to be done at the job submitter level, and this is the flow chart. It is more or less something similar which I discussed. It will check for three conditions: whether the job was finished successfully, then if it is finished successfully, all is good. Then whether the job was terminated, but if it is terminated successfully, we will stop. If it is not terminated successfully based on your log, if it was terminated due to some failure or due to some wall time limit, then you need to restart. You need to bring in the checkpoint restart mechanism, and then resume your settlement mapping or object detection workflow from the point where it was failed. Now let me show you the graph as a last slide, where we will see these three scenarios, and then we will stop the discussion. So if you remember that we have the six jobs, job 0 to job 5, and I took two example images, and these brown and blue lines represents their timelines, basically their processing timelines. When we started the job, and this triangle represent the timestamp where the for that particular job when we took the checkpoint. So you can see that the checkpoint intervals were different. For independent job, they were taken at different times. So it based on the size of the data that you are writing, and the network, what was the t optimum for that particular job. So it is independent. Now, let's take only three specific examples, and then we stop. So job 0, you see that when it started and when it finished, it was finished successfully. There was no, termination. There was nothing. It was finished successfully. Throughout its lifetime, it took two checkpoints. One checkpoint was here, and the second checkpoint was here. So basically, it took the two checkpoints, and it was terminated successfully. So that was the first scenario. Now the job 2, if you see, so job 2 took little bit more time. You can see that job 2 images were, if you try to, recall that cluster, job 2 is somewhere in between. So job 2 images sizes were more as compared to job 1. That's why it took little bit more time. But what happened that at this particular point, since this job 2 was basically hit by the wall time, it the scheduler terminated the job. But our job submission script, since it was continuously inspecting the job, as soon as it found that the job was terminated, it activated the checkpoint restart mechanism. It checked the log, and it found that the output was not, output was partially filled. The output that we are writing, it was partially filled. And then from the point it was, failed, it resumed the job for the remaining part of the data. So it did not start from the beginning. It start from the point when it failed, and then it resumed from that point onwards. So then after that it was like finished within some time, within 15 minutes or so. So that was the third scenario, basically, uh, where the job was terminated due to the scheduling policy, due to the wall time limit. And then third and last scenario was the failure. So basically, let's take an example of the job 5. So if you recall, the images in the job 5 were of very large sizes, 40,000 cross 40,000 or 46,000 of number of rows and number of columns. So they kept running for 6 hours, almost 6 hours actually. So initially, those images were terminated. Those not images, but the job was terminated because it hit the it hit the the wall time limit. Then again, checkpoint, our job submitter module invoked the checkpoint restart strategy. It found that it was half finished, so it resumed the job. But unfortunately, something happened at this particular point, and after taking the first checkpoint, after some time, this job was again terminated due to some runtime failure. So this did not happen physically. We actually forcefully terminated that job to simulate the node failure, basically. So that's why it is represented in the red. And again, checkpoint restart mechanism came into picture, and it resumed the job from this particular checkpoint. So basically, in this case, this much amount was wasted, this much work was wasted. But again, since we had written some checkpoint, we were able to save this much amount of log or the output data. So then from there onwards, it ran successfully, and with it again hit one more wall time termination due to wall time limit. After that, again it was resumed successfully and finished the entire job. So these were the this was the way through which we were able to address those challenges which I mentioned. And since so there were two big things: optimum resource utilization and making it fault tolerant. So by distributing the job into different groups based on their sizes, we we avoided the situation where job zero resources or job one resources were ideal for several hours while job five was running. So right now, job five and job one and job zero, all the other jobs are independent. So as soon as job zero is finished, the nodes of the GPUs that were being used to execute this job zero, those resources were released. So they can be used for any other job for any other user. That's how we address the resource utilization. And through this checkpoint restart mechanism, you through the optimal checkpoint interval timing and all, we were able to make the workflow fault tolerant also. So that was the preliminary work that we did for the settlement mapping workflow. And I think that was about which I wanted to present discuss with you today. So I'm happy to take any questions if you have.
Participants, you are feel free to ask any question. You can unmute yourself and ask your question, or you can post your question in chat box. Sir, I
So
think
specifically, there are two things. One thing is, uh, yeah, are there any questions?
no, sir. Uh, yes, Asra ma'am, you can ask your question.
There's someone.
Hello, good evening, sir. Sir, it was a very informative session. Thank you so much. I have a question in a sense. So, can you suggest some good books regarding, because you have discussed so many case studies at how we can deal these problems. So, is there any book which you can suggest to us where we can further read these case studies?
So basically, it will be slightly difficult to find all the possible applications in at one particular place. But I think the good approach would be start with some uh, book related high performance computing. So if you see that high performance computing will have a standard, it's a very old field and it has developed over the years. So you will find very good books on high performance computing that will give the technical aspect of this particular thing. But now, if you want to get the application side of it, then I think there is a conference called supercomputing, uh, and there is a journal called Journal of Supercomputing. So those are the two venues, uh, and I think there is a conference in India which is called HIPC, High Performance Computing something HIPC, which is I think being happened in December or January. I'm not sure, in Bangalore. So these are the some of the conferences which you can refer to the papers that are being presented. Even if they are not accessible, that's fine. At least you will get to know the abstract title. So those type of, and specifically look for the application. So the high performance computing books, I think you will get the standard books. I don't have any specific name in my mind right now, but I can share with the organizer if I find some books. But for the application side, I think it is a best strategy to look at the conferences and the journals, because they typically tend to publish papers along with the techniques. So basically, one of the journal is where we published our paper. So it is CCP, Concurrency and Computation Practice and Expertise. So this is another journal where you will see people publishing paper which has both the angles, application as well as the technical. So I would say that strategy might work well. If you
Okay, thank you, sir.
Uh, Participants, are there any queries?
So basically, these were the four challenges which I posed in towards the beginning, and in this talk, I touched upon these first two challenges: preventing data loss by making the workflow fault tolerant. That is very important thing, and then avoiding this long tail effect by making fair resource utilization. So those were more or less, common in any type of uh, work application work that we typically do on HPC using HPC.
I think there are no more questions, sir.
Sure, sure. Yeah.
Shaila ma'am?
But let me know. I mean, if there are any questions, if I'll share my. So this is my Gmail ID. I'm happy to. Uh, yeah, I'm happy to share. I'm happy to discuss anything if you have any questions or any thought about the topic.
I have shared your email ID in the chat box, sir.
Okay, nice, nice. Thank you.
Ma'am, your mic is off. Shaila ma'am.
Yes. Sorry. I would like to express our deep gratitude to our esteemed speaker, Dr. Kuldeep Kurte, for sharing his valuable expertise and practical insights. Your thorough explanation of optimization strategies and your ability to simplify complex concepts have greatly enriched our understanding of high performance computing. Thank you, sir. Please accept our virtual token of appreciation.
Yeah, thank you so much for the invitation. And I think I hope whatever little experience that I have in this high performance computing area would help you or encourage you to uh, do some work in that area. So feel free to email me. I'll be happy to discuss any questions you have, any thoughts you have.
Definitely, sir. Thank you, sir. We will also like to acknowledge and express our thanks to all the attendees. Your presence has made this session all the more meaningful and memorable. Thank you all. We will meet again at tomorrow's session at 6 p.m. Thank you and have a good day. Thank you, sir. Thank you all.
Thank you so much. Yeah, have a good day.
Thank you, sir.
Thank you, sir.